Today's lesson is about partial derivatives with chain rules. Since we have done some chain rules in the previous video, this topic should be quite easy to understand. The thing is, here we are going to work on some examples with multiple layers of chain rules, so please underline right here that we are going to work on multi-layers in this lecture. Well, what does that mean? Multiple layers of chain rules? This might be the first time that you have heard of these terms, right? That is okay. Let's find out about that in this first example. Example number 1. When you look at this example, we have quite a lot of information to think about. We have these equations, but first, let's focus on the one on the left. So let's look at this. Here we have this z equal to x squared y minus xy cubed. By now, you should know that this is a function of x and y. Alright, so please write it right here, function of x and y. In the end, this function value got assigned to this variable of z on the left-hand side of this equation. This means that this z right here that you see in this equation is different kind of variable when compared to x and y. X and y are inputs to this function. The values of x and y can change the value of f, the value of the function. On the other hand, z does nothing except receiving the value from the function. So, different kind of variable that we are looking at here. Alright, so this is the first set of information that we have in this example. But it turns out that this is not the only one. We have more on the right-hand side. So let's take a look at these equations on the right. So we have this y equal to e to the power of t, and then x equal to cosine t. When you see something like this, you should realize that in this case, y depends on the value of t. Alright, and same for x. X depends on the values of t. If you change the value of t, then the values of x and y are going to change too. This means that x and y depend on t. And in other words, x and y are functions of t. Functions of t. Okay, now at this point I want you to compare the left equation and the right equation. On the left we have a function of x and y, which means that z right here depend on the value of x and y. And then on the right hand side we have this y and x right here depend on the value of t. I think at this point some of you might have noticed the connection between all these variables. But before we talk about all these relations, let's take a look at what we need to find here. dz by dt. Alright, we need to find this first order derivative of z with respect to t. The first thing I'm going to talk about here, oh by the way, we are supposed to find this dz by dt at t equal to 0. So in the end, don't forget to plug in t equal to 0 into your dz by dt. Alright, back to this dz by dt. The first thing I want to point out is that what you are looking at here is a regular derivative. You are looking at this regular d. So this is regular diff, okay? So regular diff is used for single variable function. So make a note right here, this is for single variable. Alright, and this is different from the ones that we just worked on. dz by dx, in the previous video we have this dz by dx, dz by dy. These are partial derivative. So make a note right here that these are partial diff, and we use them for multivariable functions. Okay, so what you see right here, dz by dt, a little bit different from the partial ones. Now, at this point, we are supposed to find this relation between z and t. So we want to find this dz by dt. So let's put a meaning to this. What this means is that we want to find the change of the variable z with respect to t. Alright, so we want to find out what happens between them. But it's going to be a little bit tricky here because they turn out to be in different equations. So let's take a look here. Z is only on the left-hand equation right here, and T is only on the right-hand equations right here. And they are never in the same equations. So we are going to have to do something to connect them together, all right? Because right now they are separate. So, and the best way to do that is to use the variable map. So let's do it right here. Let's call it variable map. And it's going to be a map that shows the relation between all these variables. So I'm going to start with Z in this map. All right, Z. So I take a look at this function and I can see that for this Z, it has two inputs. One is X. X is the input for Z, and Y is also an input to Z. In other words, Z depends on the value of X and Y. Alright, and what you are looking at right here is the first function, and we know this is multivariable. Multivariable. Or in other words, we have this f of X and Y. And we are going to call this relation the first layer of function. The first layer. I told you we are going to work with layers here, so here comes the first one. Alright, now let's take a look at the next set of the equations we have right here, y and x. What you see right here is that t is going to be an input to y, so we have another variable right here. T is going to be an input to y, right? And this same t is going to be an input to x as well. Alright, so, alright, please let me fix on this. This doesn't look good. So we have this t right here. Oh, I'm sorry. Okay, t right here, and t is an input to y, and t an input to x. So what you are looking at here is a function of just one input, t. And since this is just one input, this is single variable function. And what you are looking at here is the second layer of function. Right? Coming from the top, which is z, and comes down to t at the end. Alright, so back to what we need to find here. dz by dt. We want to find the change of z with respect to t. In other words, we want to find the relation between this z to this t. But it happens that between z and t, we don't have a direct connection between them. In order to go from z to t, we are going to need to go past x or y. So in this case, I am going to find the change of z with respect to t through x first. So I'm going to travel on this path first. So let's take a look here. So in order to find the change of z with respect to t, I am going to find the change of z with respect to x first. Alright, z goes to x, so dz by dx. Alright, and then after that I move from x to t, and that is going to be the change of x. Oh, I'm sorry about the color. The change of x with respect to t. Alright, now let's take a look at something here. I use this partial right here, partial diff, because when it comes to this z, we are working with multivariable. Alright, but when I differentiate x right here, I use regular d, because when it comes to x and t, it's a single variable right here. So don't be surprised that sometimes you see this partial diff and regular diff in the same expression. Alright, this depends on the kind of function you are working on, whether it's multi or single. Alright, so what you are looking at here is the change of z through x variable. Through x. Okay, so that is the first terms of change, but it happens that this is not the only path that we can take. In order to find the change of z with respect to t, we can take the path that goes through the y variable. So this time, I'm going to go through this y instead. Find the change of z with respect to y, and then y with respect to t. Alright, so the first thing right here is going to be the change of z with respect to y times the change of y with respect to t. Okay, so two terms of change, one through x and the other through y. So make a note right here, this is the change of z through y. Alright, you can't just take one of them, you have to consider all of the paths that is available from z to t. Okay, now that we have this expression, we can work on this to find the answer for this example. Alright, starting with the variable map, now we can get the expression and we can proceed to find all these terms. So I'm going to continue with this equal to. Alright, so the first term is going to be partial diff of z with respect to x. So I take a look at this and I diff this z with respect to x. So of course I am going to get this 2xy for the first term. Alright, first term right here, diff with respect to x, and then I diff the next term with respect to x, I get y cubed. So this is going to be minus y cubed, and that is the first term. Now I need to find this dx by dt, which is the next term, and I just need to diff this x right here with respect to t. So I need to diff cosine t with respect to t, and of course I get minus sine t. Alright, minus sine t for the second term. Okay, so these two terms are for the x path. Then we look at the y path. The first term for the y path is dz by dy. So I need to diff this z right here with respect to y. So I take a look at this, diff this with respect to y, I get x squared. Alright, and then the next term I need to diff this with respect to y. So I'm going to get 3y squared out of that. So minus x is going to be the same, minus x, and then I get 3y squared. So I'm going to put y squared right here and 3 right here. Okay. Now that is the dz by dy. Let's find dy by dt. So I'm going to take a look at this y right here and diff this with respect to t. And as you know, if you diff exponential of something, then you are going to get this same exponential out of that. So here it's going to be e to the power of t. E to the power of t, and that is the last term. There you go, and what you are looking at right here is dz by dt. And now they want to find this dz by dt at t equal to 0. So let's find t equal to 0. So put this condition in, t equal to 0, then find out what happens. Then y at time equal to 0 is going to be e to the power of 0, and that is equal to 1. Now x at time equal to 0 is going to be cosine 0, and that is equal to 1 as well. Now I can find this dz by dt at time equal to 0 by plugging all these numbers in. T equal to 0, y equal to 1, and x equal to 1. Alright, into this expression. So I have this 2, 1, 1, minus 1 to the power of 3. And then I have this minus sine 0. Okay. And then I have this plus 1 minus 3, 1, 1 square, and then e to the power of 0. Now let's take a look at these terms. Sine 0 is equal to 0, right? Which means that the whole term in the front is going to be 0. That's convenient. So we got rid of that term. Now let's take a look at the back here. We are going to get this 1 minus 3 times 1. So in the end, we have this minus 2 as the final answer for this example. As you can see here, as long as we have the right variable map, then we can use that to find the formula for the derivative. And once we have the formula, then finding the dz by dt can be done quite easily. Now let's move to the next example, number 2. Example number 2 right here has a function that is a little bit different from the one that we just did. So let's take a look here. So here we have this w equal to tan of xz, and we have this z divided by y later. So as you can see here, we have 3 variables on the right hand side of this equation. We have x right here for number 1 of the variable, and then we have number 2 right here for y, and then number 3 for z. So we are looking at a function of 3 inputs, x, y, and z. Alright, so make a note right here, this function has 3 inputs. 3 inputs, variables. Okay, so in the end, this function value got assigned to the w on the other side of the equation. It's a little bit strange because in the previous example, z is a different kind of variable when compared to x and y, but in this case, they are the same. They are all inputs. X, y, and z are all inputs in this example. Alright, that is the first set of the information that we have here. Let's take a look at the one on the right hand side. On the right hand side, we have some equations, and the first one is x equal to t, and then we have y equal to t squared and z equal to sine 3t. And as you can see here, we can tell that all of them, all x, y, z depends on t. X depends on t, y depends on t, and z depends on t, which means that all of them, x, y, z, are a function of t. Alright, in the end, we need to find this derivative of w with respect to t. And once again, the tricky part is that w and t is not in the same equation. W is right here on the left equation, and then all the t's are right here, never in the same equation. So we need to rely on the variable map to find that. Alright, let's start with the variable map. We are going to find the relations between all these variables, all of them. So I'm going to start with w right here, w at the top. So as you can see here, w is a function of x, y, and z, which means that w has 3 inputs. One is x, the first input, then w has this second input, y, and then we have this z right here. Oh, let me change this to the blue. So we have w at the top, w right here, and then w has 3 inputs, x, y, and z. Okay, and what you are looking at here is a function of 3 inputs, so let's make a note right here that this is a multi-variable function. Multi, and this is function of x, y, and z. And since this is the first function that we are working with, so let's call this first layer. Okay, so the first equation is done. Now let's take a look at the second set of the information we have right here, all these equations. X depends on t, y depends on t, and z depends on t, which means that we need to include t into this map. Alright, x depends on t, so t is the input to x, t input to y, t is input to z. Alright, and now we try to find the dw by dt. dw by dt. Let's put a meaning to this. dw by dt is the change of w with respect to t. So we want to find the relation between this w right here and this t right here. And as you can see, between them, they do not have a direct path connect them together. So we are going to have to rely on the paths that go through other variables. Alright, so dw by dt right here, we are going to find the change of that. So let's first start with the first path on the left hand side. So I am going to follow, oh by the way, let's make a note right here that this is f of t. Since we only have one variable right here, so this is going to be single variable function. And let's call this second layer. Okay, now let's follow the paths. The first path is going to be the one on the left hand side. I am going to find the change of W with respect to X. So change of W with respect to X is going to be dW with respect to X. I am using a partial derivative right here because W is a multi-variable function, so it has to be partial diff. Alright, and then I continue from this path to T. Change of X with respect to T. And it's going to be this change of X dx by dt. The reason that I use regular differentiation here because we are working with X, which is single variable function. We are working with single here. Before we worked with multi-variable. Alright, so don't get confused about the difference of these signs. Now let's take a look at the next term. We have covered the first path, then we have to do the second as well. So I am going to find the change of W with respect to Y first, then change of W partial diff again with respect to Y, and then continue on this path to T. Change of Y with respect to T. Change of Y with respect to T. Alright, and that is the second path. And you know it's not complete until we cover the last path. We need to cover all the changes that can happen between W and T. So W to Z, so it's going to be the change of W with respect to Z. And then we continue on this path to T, change of Z with respect to T. Change of Z with respect to T. Once again, I am using regular diff here because we are working with single variable function. So there you go, we have the formula for dW by dt. After this, it's going to be simple, hopefully. Alright, we are going to need to find all these 6 terms. So let's start with the first one. We are going to find dW with respect to X. So we are going to need to diff W with respect to X. So this dW dt right here, the first term is going to be this W right here, and we need to diff this with respect to X, and we see X right here alone in tan. So the first thing I'm going to do here is to diff tan, and I get secant square. I keep the inside alone, and then I need to diff the inside of this with respect to X. I get Z. Make a note right here that Z right here comes from chain. Alright, so then I need to diff this Z divided by Y with respect to X, and of course that is going to come out to be 0 because this is a constant. Z and Y are constant in this case. Alright, that is the first term. Easy. So let's move to next term, dx by dt. So next term is dx by dt. So I am supposed to diff this x with respect to t. So x equal to t, diff t, I get 1. Also easy, even easier than the last one. Alright, now next term, dw by dy. Diff w with respect to y. So I take a look at this w right here, I see y right here. So these term, I can change this to z times y to the power of minus 1. So we need to diff this with respect to y. I don't need to do that here because this doesn't have y in there. It's going to be a constant. If I diff this with respect to y, it's going to go to 0. So I only need to diff this term, z times y to the power of minus 1, and I can use the power rule. Power comes down, and then z stays the same, and the power of y decreases by 1. So I am going to get minus 2 right here. Okay, now let's find the next one, dw by dt. So all I need to do is to diff this y equal to t squared with respect to t. And of course I get 2t out of that. 2t plus next term. I hope I have enough space for this. I need to diff W with respect to Z. So let's take a look here. Need to diff this with respect to Z. Okay, we have a lot of things going on, so let me erase this, all of this. So we have Z right here and also Z right here. So we need to diff these two. So the first term is going to be, I don't think I have enough space, so let me squeeze things in. So let me write this again. dw by dy is going to be minus z y to the power of minus 2. Alright, and dy by dt is going to be 2t. Alright, now plus next term dw by dz. So I'm supposed to diff this with respect to z. So I'm going to get secant square first, and I leave the inside alone, xz, and then I diff the inside with respect to z. I get x. Okay. Alright, make a note right here, x. This x comes from chain. And then I need to diff this z right here. And since this z is at the numerator of the fraction, I can just diff it to be 1. So all I get from here is going to be plus 1 over y. Okay, don't forget to put parentheses to this because this is about this term. Okay, now let's move to the last one, dz by dt. I need to diff this with respect to with respect to t. So diff sine 3t with respect to t, I am going to get 3 cosine 3t. So put it right here, 3 cosine 3t. Alright, just enough space. Okay, in the end, I need to combine these terms together to make it look a little bit nicer. So this is going to be equal to z at the front, secant square xz minus 2tz, okay, minus 2tz, 2tz, okay, divided by y square. Alright, and then we have this whole term, so you can keep it plus 3 at the front, and then we have this secant square xz with x, and then plus 1 over y cosine 3t, and that is the final answer for this example. Let me check again with the solution I have whether it's correct, and it turns out to be okay. So this is correct. Now same concept as the example one, right? Find the variable map, then find the formula, and then use the formula to find the derivative. Alright, now let's use this same concept again on example number 3. Each one of this is going to be a little bit different from one another. So let's take a look at number 3 and find out how it's going to be different this time. So first, I am going to look at the equation on the left hand side. So here we have this w, and on the right hand side of this equation we have 2 variables. So even though we have w right here, it doesn't imply that we need to have 3. So here we are going to looking at a function of 2 variables, x and y only. Alright, so in the end, this function value got assigned to this w instead of z. Need to keep that in mind. Okay, now what about the information on the right hand side? We have this x equal to u squared plus v squared, and then y equal to 2uv, which means that both of these x and y depend on both u and v. So we are looking at a function of u and v right here. As you can see, the second set of the information here is a multivariable function, which is different from the previous one. Alright. Now, in the end, we are supposed to find this dw, partial diff of w with respect to u, and then partial derivative of w with respect to v. But once again, we are going to use the same concept. Find the variable map, find the relation between all these variables, and then we can use them to find the formula. So let's start with that. Same thing, variable map. Variable map. Okay, I'm gonna start with W again at the top, and I know that W has two inputs, which are X and Y. X right here and Y right here. Since we have two inputs, we are looking at a multi-variable function. Make a note right here, multi-variable. And this is the first function that we are working with. Let's call that first layer. And this is a function of X and Y. Now, about X and Y, X depends on two variables, U and W. So in this case, we have two variables in this set of equations, U and W. So we are going to have this, so put U and W like this. So X depends on both U and, U and V, all right? So X depends on both U and V. So we are supposed to put this U pointed to X because U is one of the inputs of X and V is also an input to X. Once again, looking at Y right here, Y depends on both U and V. So U is going to be input to this Y, and same with V. V is an input to this Y as well. And we are looking at a second layer of function. And in this case, we have two variables, which means that this is going to be multi again. Right? So this is a function of two variables, U and V. And this is the main difference between example 3 and the previous ones. The previous one, the second layer, is just single variable. Right now we have multi again. So let's find out what we need to find for the answer for this example. We are supposed to find this dw by du. So let's find that. dw by du. Let's make a note right here. This is the change of w with respect to u. Okay, so we want to find the relation between w and u. So this and this. So in order to find the relation between them, we need to follow all the paths that connect them together. So the first one is this, w to x and then x to u. Okay, so let's work on that. Work on this expression. W to x, change of w with respect to x. I am working with multivariable, so I have to apply partial diff. W by dx. And then the next term is dx by du. And once again, I am working with multivariable. So the next term has to be partial derivative of x with respect to u. Alright? Now, next term, the next path that we have is going to go through y. Change of w with respect to y. Change of w with respect to y. Alright? And then continue from that, change of y with respect to u. And this time again, it's a multivariable function. So it's going to be partial derivative of y, partial diff of y with respect to u. So there you go. You have this first formula for the derivative with respect to u. What about we use this right away? Alright, let's find the first one, dw by dx. This is going to be equal to, alright, dw by du equal to the first term. I am going to diff this with respect to x. This one is easy. Diff this with respect to x, I get 3x squared. So I get 3x squared. Diff y cubed with respect to x, it's going to go to 0. Alright, that is the first term. Then the second term, dx by du. I need to find this partial diff of x with respect to u. So I need to diff this with respect to u. And since we focus on u only, we are going to get 2u out of that, out of this term. I diff u squared, I get 2u. But if I diff v squared with respect to u, it's going to go to 0. Alright, easy. So let's move to the next one. dw by dy. So I am going to diff this w right here with respect to y. So as you can see here with y cubed right here, we are going to get 3y squared out of that. Okay, next term, dy by du. So we are going to diff this with respect to u. Of course, we are going to get 2v out of that. So it's going to be 2v right here. Okay, so let's put all the terms together. So here we are going to have this 6x squared u. 6x squared u plus 6y squared v. Alright, for the answer, the first one, dw by du. Alright, next one, we are supposed to find the first derivative, the first order partial derivative of w with respect to v. Why don't we start with the formula? The first order partial derivative of w with respect to v. So we are going to have to find the relation between w and v. Alright, w and v by following all the path that connects them together. All the path that connects w to v. And as you can see here, we have one path over here on the left hand side. Change of w to x first, and then x to v. So this one, change of w with respect to x first, and then change of x with respect to v later. Alright, that is the first path. And then the next path right here on the right hand side, change of w with respect to y first, and then change of y with respect to v later. So here we have this dw with respect to y first, and then dy with respect to v at the end. And there you go, we have the formula for the second value of the derivative. Now we are going to use this to find the value. So here dw with respect to v is going to be equal to, let's find all these terms really quickly. dw by dx, we have found that up here, and it's going to be equal to 3x squared. So we can reuse that, 3x squared. And then we are supposed to find partial diff of x with respect to v. So we are going to have to go here and diff this with respect to v. And as you know, we are going to get 2v out of that. Plus, next term, dw with respect to y, we have found this right here. And it's going to be equal to 3y squared. So reuse that, 3y squared. And then next term, dy with respect to v. So we are going to diff y with respect to v. This one with respect to v, of course, we are going to get 2u from that. So let's conclude this one. And here we are going to get 6x squared v plus 6y squared u for the second answer. So there you go. We have found two first order partial derivative of w with respect to u and to v in this example. Alright, let's move to the last example of this lecture. Example number 4. Alright, and it's going to be the most challenging one. Alright, let's take a look here. Once again, we are going to check out the variables really quickly. The first one here, we have this w equal to x ln of yz squared. So we are looking at function of three variables, three inputs, f, x, y, and z. Three of them, and then the function value got assigned to this w in the end. Okay, so that is the first relation that we know. Now let's take a look at the next set of the information. The equations on the right hand side here, we have this x equal to square root of u. So we have u right here. Y equal to e to the power of 2v. We also have v. And then z equal to v cosine u. Alright, v and u. So we have u and v for the second layer. And for the first layer, we have x, y, z. And in the end, we are supposed to find the first order partial derivative of w with respect to u and to v. Of course, it's going to be tricky again because w and u is never on the same equation, and same with v, because v is right here and w is right there. So we are going to have to repeat the whole thing again by using the variable map. Start with the variable map to find the relations between them. Map, okay. Once again, we are going to start with the top one, which is w. W right here has 3 inputs, so we have x, y, and z. We are looking at a multi-variable function, so let's make a note right here that this is a multi-variable. Which means we need to apply partial derivative. So this is function of x, y, and z. And this is the first layer of function. Now let's take a look at the next set of the variables. We have u and v. So we are going to put u and v like this right here. So let's find out about this x first. X has 1 input, so it's going to be just u. So u is the input to this x. So let's take a look here. U is the input to this x, but not v. Just u. Alright. Now let's take a look at y. Y has 1 input, which is v. So this v right here is the input for this y. Alright. Not for, u doesn't have a part right here. So just v for this case. Alright, and in the end, z has 2 inputs, v and u. Okay, so in the end, z has 2 inputs. It's going to be u right here and v right here. So you are looking at both single variable and multi-variable. For the x, it's going to be single variable because it has only 1 input of u. So make a note right here, x right here, this is single. For y right here, also single because y only has 1 input, which is v, but z right here has multi variable function because they have 2 inputs, multi-variable, and we are talking about second layer here. So in this case, we have some varieties in the second layer. So we have both single and multi, so keep that in mind. This one, f with 1 input of u. This one has 1 input of v, and for this one has 2 inputs of u and v. Okay. Alright, so let's start with the first one. Partial diff of w with respect to u. So we are supposed to find the formula for that first. We are going to find the relation between w and u. And just like the same, we are going to follow all the paths that connect w to u. So let's find them. Connect w to u and find all of the paths. So the first path is going to go from w, right, to x, and then x to u. So that is the first path. dw, this is supposed to be change of w with respect to x, and then change of x with respect to u. That is the first path. Once again, I use this regular diff because we are working with single variable function for the second layer. Alright, now let's take a look at, let's check whether we have other terms for this expression. Alright, we have to find other path that connects w to u, and as you can see here, we have another one right here. W to z, and then z to u. Okay, dw to dz, and then dz with respect to u. This is the difference. When I diff this z, I use the partial diff because for z it's going to be multi-variable. So I need to point out this difference. Right, this is partial diff. Alright, I don't need to do anything with y, because if I go along with y, it doesn't go, as you can see here, if I go along y path, it doesn't go to u. Right, so I don't need to consider this path along with y. So that is it for the expression for dw by du. Let's use it right away. Okay, so this is going to be equal to right, dw by du equal to the first term. Let's work on this one. dw by dx, so we are going to diff this with respect to x. So we are going to treat the back term as constant. So in the end, we are going to get this ln yz square out of that. Alright, now next term, dx by du. I need to diff this x right here with respect to u, and as you know, I am going to get this 1 over 2 square root of u. Alright, that is the second term. Now next term, I need to find dw by dz. dw right here by dz, so I need to diff this with respect to z. Z is inside the ln, so I need to diff ln first. But first of all, I am going to keep x as constant right here, and I diff ln, so I get 1 over yz square. And then I need to perform the chain rule inside this ln. Diff this with respect to z, I get 2yz. I get 2yz out of that. Okay, so that is it for the third term right here. So the last term, dz by du. So I'm supposed to diff this z right here with respect to u. So here I diff cosine u. I am going to get minus sine u. So for this one, it's going to be minus v sine u. So let's conclude on this one. This is going to be equal to, by the way, we can cancel some terms here. Z square right here to this one, and y right here to this y. So in the end, we have this ln of y z square divided by 2 square root of u. Alright, for the second term, we have this, alright, 2xv sine u divided by z. Oh, by the way, we have this minus sign, so this has to be minus. Alright, so that is the first derivative that we need to find. Let's find the second one. The second one is dw by dv. So we are going to have to find the expression for that right here, dw by dv. And it's going to be equal to something, and we need to find that by using the variable map. We need to find the relation between w and u right here by following all the paths that we can find between them. Alright, oh, by the way, oh, sorry, not u right here. It's supposed to be v, between w and v. So we need to follow all the paths. And as you can see here, we have two paths that connect w to v down here. One through y right here, dw with respect to y, and then y with respect to v, and then, okay, let's work on that one. dw with respect to y, and then change of y with respect to v. So I use this regular differentiation here because y right here is a single variable function. Okay, so that is the first path, but then we have another path on the right hand side. We have this path coming through the z variable. Change of w with respect to z, and then change of z with respect to v. So let's put that into the expression. Change of w with respect to z, and then change of z with respect to v. Alright, so let's put a box around that and perform the calculation. So this one is going to be equal to dw with respect to v equal to, first term, diff w with respect to y, so we are supposed to diff this with respect to y. So I'm going to keep x as constant in the front, and then I diff ln, so I get 1 over yz squared. And then I need to perform chain rule. To diff y inside, of course I get z squared out of that. Right? Z squared out of that. Next term, I am looking at this dy by dv. So I am supposed to diff y with respect to v. I need to diff this y with respect to v. So diff e to the power of 2v, you get 2e to the power of 2v. So here you are going to get 2e to the power of 2v. Okay, next term. Here we are going to need this dw by dz, but we have found them before right here. So let's reuse that. It's going to be x times 1 over yz squared times 2yz. Same thing. Alright, now next term, dz with respect to v. So I'm supposed to diff this with respect to v. So v is going to go away. I get the constant cosine u out of that. So it's going to be cosine u out of that. So let's work on these terms a little bit. Z right here is going to get cancelled, and then z right here, square right here, cancel with this z, y right here with this y. Now let's clean this up. We are going to have this 2x e to the power of 2v divided by y right here for the first term. Then for the next term we are going to get this 2x cosine u divided by z. For the answer, the last one, alrighty. So there you go. Every examples that we have done here, we follow the same concept, the same guidelines. As long as you understand how to build the variable map and to build the formula out of that, then you should be fine when it comes to the partial derivatives with chain rules.